Hey guys, and welcome to this lesson all about solving a new type of equation, namely radical equations. That is, any equation that has a square root symbol, or perhaps a third root symbol, or any radical at all. And remember, to solve an equation means let's just find the value for this variable, or whatever variables there might be present, such that it'll make this equation a true statement. So in this first equation, we have the principal square root of negative 2d plus 3 minus 3 equals 4. And so we need to find out the value of d that's going to make this true. And of course, the big difference here is we've got this square root symbol here. And so my question is, how are we going to kind of liberate this negative 2d plus 3 so that we can kind of work with it a little more and eventually isolate that d? Well, I think that the inverse operation of a square root, the way to get rid of a square root is by squaring it. Right? For instance, if I had the square root of 5 and I squared that, we just get 5, right? By definition. If I had the square root of 10 and I squared that, well, we get 10. So we know there's going to be some squaring involved in this problem. And I'll say it's really, really tempting to go ahead and say, well, let's square both sides of the equation right now. But beware. I'm going to walk us through this first problem, and then I'll tell you why that wouldn't be such a good idea. So what I suggest, and this is going to be our general strategy, is let's isolate this radical on one side of the equation first. And to do so, all I think we need to do is add 3 to both sides of our original equation, yielding this new equation. The square root of the quantity negative 2d plus 3 equals 7. So what we're going to do now is, well, if the square root of negative 2d plus 3 is equal to 7, well, then if I raise this side of the equation to the second power, I should get just negative 2d plus 3, right? By definition, and please do write an extra line here. I know I've got the copy-paste feature, so it makes it easier for me. But if I take that square root and I raise it to the second power, by definition, we should get negative 2d plus 3 on the left-hand side of the equation. By definition, if I take a square root of some quantity and I square it, I get that original quantity. Of course, we had an equation to begin with, so whatever we do to the left-hand side, we must also do to the right-hand side, and we end up with this nice-looking equation. We have successfully gotten rid of this square root symbol, and we put ourselves in a position to isolate this d no problem. Here, it should just be, smooth sailing. I think we're going to subtract 3 from both sides of the equation. We end up with negative 2d is equal to 46. Dividing both sides of this equation by negative 2 should yield us our solution to the original, namely d equals negative 23. And always, 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 let's do a quick check to make sure that that actually works. If d were equal to negative 23, negative 2 times negative 23 is positive 46, plus 3 is positive 49. The principal square root of 49 is positive 7, minus 3 is 4. That's awesome. I do want to make a note that some people, they have the urge to immediately go ahead and square both sides of our original equation. I'm going to zoom kind of way in here. They have the urge to do this. They say, oh, well, if I square the left-hand side and I square the right-hand side, right, won't I just get negative 2d plus 3 minus 9 equals 16? Careful, 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 careful. If we were to actually square the left-hand side of the equation, that means take that whole left side of the equation, negative 2d plus 3 minus 3, and multiply it by itself. Right? They say, that's what it means to square something, right? Multiply it by itself. And note that when you do this, yes, this term times this term, we will lose that radical, right? We will get negative 2d plus 3. But there are 4 steps of multiplication here. We're going to get a product that has all sorts of radicals still in it. I call this a whack-a-mole situation, right? You whack 1 mole, so you get rid of one of these radicals, but it just pops up somewhere else. So beware, before you raise to the second power, in this case, do isolate that radical. That is going to be our general strategy. We want to do whatever we need to get that square root or that third root or whatever root it might be by itself on one side of the equation. Then we can raise to whatever appropriate power to put ourselves in a position to isolate that variable. All right, let's take a look at our second equation. And the big difference here is we're dealing with a third root instead of a square root. But the strategy is going to remain exactly the same. Let's isolate this third root on one side of the equation first. And to do so, I think we're going to want to add 2 to both sides of the equation, yielding negative the third root of the quantity x minus 6 equals 5. And while we could raise to the third power right now, and we'd have to be very conscious of this negative 1 out in front here, just for good measure, I'm going to multiply both sides of this equation by negative 1 first. So we have just regular, the third root of the quantity x minus 6 equals negative 5. So we've got the third root of this number, whatever number that is equal to negative 5. Well, I want to know what x minus 6 is. I don't want to know what the third root of x minus 6 is. So what I think we can do now is we say, all right, if we raise the left-hand side of this equation to the third power, by definition, if I took the third root of this quantity and I multiply it by itself 3 times, by definition, we will now get x minus 6. That's what it means to be a third root of something. But of course, what we do to one side of the equation, we must definitely do to the other side of the equation. Negative 5 raised to the third power is negative 125. And I think from here it's smooth sailing. Let's just add 6. Boom. We end up with x equals negative 119. And of course, always a good idea to check our answer. If x were negative 119 minus 6 is negative 125. The third root of negative 125 is negative 5. Negative 2 minus negative 5 is indeed 3. So I hope we're getting the hang of it. One more thing I want to put on your radar in this third example. So hopefully you know what to do. So let's get right into it. I think we want to isolate this square root first. Let's subtract 5 from both sides. We get that the principal square root of 3g minus 7 is equal to negative 4. But I don't want to know what the principal square root of 3g minus 7 is. I want to know what 3g minus 7 is. So I am going to raise the left-hand side of this equation to the second power to get, well, 3g minus 7. Awesome. 3g minus 7 is equal to, and of course what I do to one side of the equation, we must do to the other, is equal to 16. And from here it should be smooth sailing, right? We're going to add 7 to both sides. And we end up with 3g equals 23. Now we're going to get a fraction as an answer. Is that okay? Of course that's okay. Divide both sides by 3. And we end up with our solution. G equals 23 over 3. Always a good idea to check our solution. So let's see what happens if we substitute 23 over 3 in for this variable g. All right. So 3 times 23 over 3, by definition, right? The 3's will simplify away. We'll just get 23. 23 minus 7 is 16. The principal square root of 16 is 4. 4 plus 5 is not 1. Wait a second. This value for g did not work in our original equation. It did not make it true. What happened? Well, this is why we always want to check our solutions, especially with these radical equations. Maybe you noticed this before, but take a look at this statement right here. This statement says that the principal square root of 3g minus 7, right, the non-negative square root of 3g minus 7 is equal to negative 4. That's impossible. This radical sign, this principal square root sign says whatever this is equal to, it cannot be negative. And what we've said here is it's negative 4. This right here is a false statement. It is not true. And that is exactly what led to 23 over 3 not working when we substituted it back in. This equation right here, maybe you guessed it, no solutions. There is no number that we are going to be able to substitute in for that equation to make it true. So you always want to check your solutions. All right, 2 more slightly more difficult examples that I want to walk you through, and then I'll have you try some on your own. So let's take a look here. The strategy is going to be exactly the same. What's different is that we have a variable within our radical symbol and a variable outside of a radical symbol. So let's see how that shows up. Well, I think we're still going to want to isolate that square root, so let's subtract 5 from both sides, yielding x minus 5 is equal to the square root of the quantity x plus 7. Just like before, we need to isolate a variable, and in doing so, or in order to get there, we must liberate this x plus 7 from its radical. So let's raise the right-hand side of this equation to the second power, yielding on the right-hand side x plus 7. That's nice, kind of mission accomplished there. And on the left-hand side, we got to do the exact same thing. We got to raise the entire left-hand side of this equation to the second power. What do we get when we square the quantity of x minus 5? We get x squared minus 10x plus 25. So we started with a radical equation with a radical symbol in it, and now it has transformed into a polynomial equation, and I hope you remember how to solve polynomial equations. We need to obtain a 0 on one side of the equation. So we're going to subtract both x and 7. I'm doing it in one step here. So that we end up with 0 on the right side of this equation, and we end up with x squared minus 11x plus 18 equals 0. So now we need to factor the left-hand side. Hopefully you know how this factors already, but that's going to factor as x minus 2 times the quantity of x minus 9, meaning that our two solutions, or potential solutions, are 2 and 9. All right, but like I said before, we always got to check our solutions just to make sure. And we have two potential solutions to check now. So let's try one out. Let's try 9. Let's try 9. So if x were equal to 9, 9 plus 7 is 16. The principal square root of 16 is 4. 4 plus 5 is 9. And x was also equal to 9, so we get 9 equals 9. This solution works. X equals 9 is a solution to this equation. What about x equals 2? If x were equal to 2, 2 plus 7 is 9. The principal square root of 9 is positive 3. Positive 3 plus 5 is 8, which is not equal to 2. So this solution does not work. And so in this case, it happened that only one of our two potential solutions worked. But sometimes they're both going to work. Perhaps sometimes neither of them will work. So there's no kind of guarantee that a specific number of them is going to work. You always got to check them both. Okay, with that, let's do one more together, and then I'll have you try some on your own. So same kind of idea here. We're going to want to isolate the radical, in this case by adding 5 to both sides of the equation, yielding the square root of the quantity x plus 6 is equal to x plus 4. Of course, I don't want to know what the square root of x plus 6 is. I want to know what x plus 6 is. So let's raise this to the second power, yielding us on the left-hand side of the equation x plus 6. Of course, when we do to one side of the equation, we must do to the other. And when we square the quantity of x plus 4, we get x squared plus 8x plus 16. We now have a polynomial equation, one in which we are going to have to obtain 0 on one side of the equation, in this case the left side, and factor whatever we have on the other. So let's see, now we've got 0 equals x squared plus 7x plus 10. Awesome, that looks like it factors very nicely. 0 equals the quantity of x plus 2 times the quantity of x plus 5. So our two potential solutions are x equals negative 2 or x equals negative 5. All right. Let's try them out. Here we go. If x were equal to negative 2, negative 2 plus 6 is 4. The principal square root of 4 is positive 2. Positive 2 minus 5 is negative 3. Negative 2 minus 1 is also negative 3, so nice. X equals negative 2 is a solution to this original equation. What about negative 5? Negative 5 plus 6 is 1. The principal square root of 1 is 1. 1 minus 5 is negative 4. Let's see, negative 5 minus 1 is negative 6, so x equals negative 5 is not a solution to that original equation. This one, like number 6, happens to have only one solution. But again, no guarantees. Sometimes they'll have 2, sometimes they'll have none. Always got to check. So I hope you got the hang of it. And what we've got here are 5 equations very similar to the ones we did just now. Why don't you pause the video, give these a try, and when you're done, play the video and see how it went.